Okay, everybody, for this section, I decided to go back to the book because I wanted to do some practice problems with you as well. So if this doesn't work out, you have to let me know in an email if you prefer the PowerPoints. However, the PowerPoints are still accessible to you in Sakai under the Lesson 1, Week 1, or under the resources. You can find them in either place. We're going to talk about conditional probability in this section, and conditional probability, for example, this is a really good example here in the objective. It talks about how approximately 15% of adult men in the United States are more than 6 feet tall. If a man is selected at random, the probability that he is more than 6 feet tall is 0.15 or 1500ths. Now, assume that you learn that the selected man is a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall comes much greater than 0.15. Now, this example hits home with me because, as some of you may or may not know, I have a lot of international students, and most of my international students play basketball. So when I go somewhere, almost all of my kids are over 6 feet tall, and it's kind of funny. But anyway, I always forget at how uncommon that is until I go somewhere and everybody's staring at us. So anyway, a probability that is computed with the knowledge of the additional information is called a conditional probability. So the condition that we found out here is that they are basketball players. And the probability computed with such knowledge, without such knowledge, if you don't know that or not given the knowledge, then that would be an unconditional probability. As this example shows, the conditional probability of an event can be much different than unconditional probability. So if my household was selected at random and they went in and measured the people in my house, the men in my house, that are over 6 feet tall, currently I have, 1, 2, 3, 4, 5 men in my house. And the only one that isn't above 6 feet tall is my husband. So the rest of them are 6'2", 6'6", 6'8", and 7 foot. So anyway, so my household wouldn't be considered a regular household, I guess. Anyway, example 15. You have Joe, Sam, and Eliza, and Maria. They've been elected to the executive committee of their college student government. So we have to choose a chairperson and a secretary. So they decide to write each name on paper and then draw them at random. Now this would be considered an SRS because in a small SRS you can put names in a hat and draw them at random. The first name drawn will be the chairperson and the second name drawn will be the secretary. So what's the probability that Joe is the secretary? So remember, that's what we're looking for. So here is the chart that shows you all of the possibilities. So table 5.3 is a sample space for the experiment here. And we have all the possibilities where we have the chairperson first, secretary second. So there are 12 equally likely outcomes. Now 3 of them, Sam Joe, Eliza Joe, and Maria Joe, correspond to Joe being the secretary. So see here where they're in, Joe is in second place here. 3 of them correspond to where Joe's the secretary. So that would mean that 3 out of 12, or 1/4, would be the probability of that. Now, let's take a look at if it's a conditional probability. So let's suppose that Eliza is the first name selected. So she, oh my goodness, sorry, I'm yawning, is the chairperson. Now that the probability that Joe is the secretary, okay, so now things are different. So when we look back up here at this chart, we see that there are 3 possibilities where Eliza is marked as the chairperson, all right? And out of those 3, only 1, Joe would be the secretary. So this conditional probability changes things. Before, when we said Joe being the secretary, he had a 1/4 chance. But now, if we take a look at the 3 possibilities, of the 3 possibilities where Eliza is the chairperson, Joe is only 1 out of 3. So the probability that Joe is the secretary, given that Eliza is the chairperson, see the difference in the wording? is 1/3. So 518 asks us to compute the probability of an event. Joe is the secretary. After giving us information about the other event, Eliza is the chairperson. The probability is called conditional probability. So this notation here is this straight line, and sometimes this straight line in other math we say we say such that. So similar, it could be, we could say such that here too. Joe is the secretary such that Eliza is the chairperson, or Joe is the secretary given that Eliza is the chairperson. So the conditional probability that Joe is the secretary given that Eliza is the chairperson. Now the conditional probability of an event B given A is denoted by P, B, such that A. All right, so the given is right here. This is what you're looking for, and this is what you're given. So the probability that B occurs under the assumption that A is definitely going to occur. We read P of B given A, P, the probability of B given A. Okay? Now, the general method for computing probabilities, we were able to take a look at the chart above here, and we saw that there were 3 possibilities where Eliza was the chairperson, 1 out of 3 where Joe is the secretary. Okay, let's take a closer look at that 1/3. So the denominator of the number of outcomes that were left in the sample space after it was known that Eliza was a chairperson, the number of outcomes where Eliza is a chairperson was 3. We already said that. Okay, I'm going to zoom back over here. 3. The number, or the numerator 1, and the corresponding to the 1 outcome in which Eliza is the chairperson and Joe is the secretary. So I say, how many times is Eliza the chairperson, Joe's secretary? 1. The number of outcomes where she is the chairperson and Joe is the secretary is 1. So the probability that Joe is the secretary given that Eliza is the chairperson would be written like this. And I just reminded you here that this would be given. We can obtain another useful method by just using the whole thing. If we take a look at Eliza being the chairperson, she has 3 out of 12 possibilities. This is another way of looking at it, okay? So another way of looking at it, 3 out of 12. And then looking at where Eliza is the chairperson and Joe is the secretary is 1 out of 12. So the probability that Joe is the secretary given that Eliza is the chairperson, you would put your 1 over 12 over 3 over 12. And you remember that when you do this, you're going to invert and multiply. So you have 1/12 divided by 3/12, which means times 12 over 3. So that will give you 1/3 again. So either way that you do it is fine. So the general method for computing conditional probabilities would be the probability of B given A is the probability of A and B over the probability of A. Note, we cannot compute the probability of B given A if the probability of A doesn't exist, or in other words, is 0. Can't happen. So if I say, what's the probability that Joe's going to become secretary when John will be the chairperson? Well, there was no John in the mix, so that can't happen. So, when the outcomes in the sample space are all equally likely, the number of outcomes corresponding to A and B over the number of outcomes corresponding to A. All right, let's look at an example, starting with table 5.5. Here we have a table that represents men and women in millions, 25 years or older, who have attained various levels of education in a recent year. Okay. The number of men and women with various levels of education. So here you have your men, and here you have your women. And when we add them up, we get 94 million men in this study. We get 101 million women. That's a lot. Okay, so let's see what we want to do here. What is the probability that the person is a man? Now I'm going to be doing some flipping back and forth here. Here we get, and what is the probability that the person is a man with a bachelor's degree? And what is the probability that the person has a bachelor's degree given that the person is a man? Okay, so the probability that the person is a man. I'm going to flip back to the bottom of this page and say the probability that he is a man is 94 million men. So we're going to take that 94 million over the total. How did I get the total? I added the men and women together here. So these two added together would be 195. So the probability that they are a man would be your 94 over 195, which is 0.4821. Part B, what's the probability that the person is a man with a bachelor's degree? Again, going back to the chart, you want to look at bachelor's degree, and man is right here at 17. Well, you can't see that. Right here, 17.5%. So that's 17.5 over the total again. So over the total of 195. So the probability that we are going to have a person with a bachelor's degree given that the person is a man. So the given that a person is a man on the bottom, we already did that. The man has a bachelor's degree, we already did that. Now notice when we invert and multiply, these are gone. So you're simply taking 17.5 divided by 94. Okay? And that'll give you 0.1862. Now I wanted us to practice one more of these. So let's take a look at the check your understanding. A person is selected at random from the population in table 5.5. What is the probability that the person is a woman who is a high school graduate? A woman who is a high school graduate. Okay. If we go back over here and we see high school graduate woman is 31.9. 31.9. And we're talking about the entire people in the study. So the probability that we would have a woman who is a high school graduate chosen would be 31.9 over 195. When I do that, I get 0.164. 0.164 here. All right, so what's the probability that the person is a high school graduate? That the person is a high school graduate. All right, the person out of the whole thing. So we got to add these two together. When we add these two together, we will get 61.5 million people. 61.5 million when we add these two together. So the probability that the person is a high school graduate would be that 61.5 over 195. And when we calculate that, we get 0.315. If you can't see this, I apologize, but 0.315. So C says, what's the probability that the person is a woman given that the person is a high school graduate? So we're simply taking this top divided by this bottom. Okay? And when we do that, again, the 195s are going to reduce. So you're simply going to take 31.9 divided by 61.5. And when you do that, you will get 0.519. 0.519. Okay? So there's another example of our conditional probability. Now, the general multiplication rule for conditional probabilities provides another way to compute probabilities for events in the form of A and B. So if we multiply both sides of an equation by probability of A, then we will get this formula. So the probability of A and B, this means and means they're both occurring, would be the probability of A times the probability of B, given that A does occur. That's the only way we can do it if they're both occurring, right? We have to say that it's given that A occurs. So, and again, the probability of A and B is also the probability of B, given that A occurs, given that, well, I'm sorry, the probability of B times the probability of A, given that B does in fact occur. So these two are the same. Equivalently, they end up being the same thing. All right? So, an example. Among those who apply for a particular job, the probability of being granted an interview is 1/10. Among those interviewed, so in other words, given that we're looking at the people who were interviewed, the probability of being offered the job is 0.25. Find the probability that an applicant is offered the job. So being offered a job involves two events. First, the person has to be interviewed, and then that person who was interviewed must be offered the job. So in the multiplication rule, we just take the probability of the people being interviewed times the probability that they're offered the job, and we get 0.025. Now, another example, it says in a certain city, 70% of the high school students do graduate. Of those who graduate, 40% will attend college. What is the probability that a randomly selected high school student will attend college? So, you're going to take your 0.7 times your 0.4, and the probability that a randomly selected school student will attend college would be 0.28. All right? Now, let's look at independence. Some cases, the occurrence of one event has absolutely no effect on the probability that the other occurs. For example, if a coin is tossed twice, the occurrence of heads on the first toss does not make it any more or less likely that heads will come up on the second toss. So, 5.21 does illustrate this fact. Let's look at example 5.21. It's a fair, you'll see they always say fair coin, and that just means no one did anything to the coin to make the weight off on one side or the other. What is the probability that the second toss is heads? Okay, well, if we think about it for a moment, we're like, well, the probability that a coin, when it is tossed, for it to be heads would be 1/2. I don't think that's going to change if I flip it twice because they're independent. Let's see what it says. What is the probability that the second toss is heads given that the first one is heads? Are the answers to A and B different? Does the probability of the second toss, whether it's head, second toss is a head, change if the first toss is a head? Okay. There are 4 equally likely outcomes for the two tosses. The sample space, again, if I'm taking a coin and I'm flipping it twice, I could get heads, heads. I could get heads, tails. I could get tails, heads. I could get tails, tails. Of these, there are 2 outcomes where the second toss is a head. Therefore, the probability that the second toss is a head would be 2 out of 4, which is 1/2. Now, if we use the general method for computing conditional probabilities, we'll take the number of outcomes where the first toss is heads and the second toss is heads, and the number of outcomes where the first toss is heads, and we still get 1/2. Now, these answers are the same, probably because the second toss is a head does not change if the first toss is a head. So they are independent. Now, we're going to jump to something a little bit different. We're going to talk about sampling without replacement. And what that means is if I have a box of items and I draw an item and I put it to the side, it's no longer in my box of items. That would be without replacement. I'm not putting it back in. So we have a box that contains 2 cards marked 0 and 2 cards marked with a 1, as shown in this box illustration. 2 cards will be sampled without replacement from this population. So what is the probability of a drawing a 1 on the second draw, given that the first draw is a 0? What is the probability of drawing a 1 on the second draw, given that the first draw is a 1? Are the first and second draws independent? Let's take a look. If the first draw is a 0, then the second draw will be made from the population here, which changes. There used to be 4 things in here, and now there's only 3. 2 of them are 1, so the probability of drawing a 1 after drawing a 0 first would be 2 out of 3. For the second one, we asked what is the probability of drawing a 1 if the second draw given that the first draw is a 1. Okay, so now this changed. Now I took a 1 out of here. I still only have 3 that are left, but if I want to know what the probability is now of drawing a 1, I only have one left. I only have one left. So the probability would be 1 over 3. Now, the first and second draws are not independent events. They are dependent upon each other. The probability of drawing a 1 on the second draw depends on the outcome of the first draw. Okay, so you have to remember that. Now, there's sampling with replacement. This would mean after every time we draw something, we throw the item back in. So it again has another equally likely chance of being chosen. So 2 items will be sampled with replacement from this population. Does the probability of drawing a 1 on the second draw depend on the outcome of the first? Well, since it's with replacement, no matter what the first draw is, the second draw will be made from the entire population. So therefore, the drawing a 1 on a second draw would be 2 out of 4, which would be 1/2, no matter what the first draw is, because we're throwing the item back in. Now, sometimes the population is so incredibly large that even though we are not replacing the item, it's not going to have that much change on the probability. So if I have 1,000 cards with 0 and 1,000 cards with 1. So same kind of thing, but I have 1,000 zeros and I have 1,000 ones. What is the probability of drawing a 1 on the second draw, given that the first draw is a 0? Same question, but different population now. What is the probability of drawing a 1 on the second draw, given that the first draw is a 1? Are the first and second draws independent? Are they approximately independent? Okay, so the first draw is 0. Then the second draw will now be made from the population of 999 zeros and 1,000 ones. So therefore, there are only 1,999 equally likely outcomes, and 1,000 of them are ones. So now the probability of drawing a 1 for the second draw is 0.50025. So you can see that, it's still about 1/2. What's the probability if the first draw is a 1, that the second draw made from that population of this, there'll be 199 equally likely outcomes, and 999 of them are 1. The probability of drawing a 1 here is 999 over 1,999. So you can see how close these two numbers are together. So even though we did it without replacement, if we were rounding to the thousands place, we would still get 50%. So the probability of drawing a 1 on the second draw depends slightly on the outcome of the first draw. So the draws, they say, are not independent. Kind of hard for me to even say that, but they are not independent. However, because there's a difference of probabilities is so small, the draws are called approximately independent. So in practice, it would be appropriate to treat the two as independent events. So you have to take a look at the size of your population. So in summary, when sampling with replacement, the sampled items are independent. When sampling without replacement, if the sample size is less than 5% of the population, you can treat it as independent. When the sampling without replacement, if the sample size is more than 5% of the population, then you cannot treat them as independent. Okay? So let's check our understanding. A pollster plans to sample 1,500 voters from a city in which there are 1 million voters. Can the sampled voters be treated as independent? Yes, they can. Why? Because if I take 1 million and I take 5% of that 1 million, 5%, if I go back one decimal, I'm going to get 100,000 is 10%. Half of that is 50,000. That is a lot less. So since it is more than 5 or less than 5%, I can treat them as independent. Now, if I have 500 students attend a college basketball game, 50 of them are chosen to receive a free t-shirt. 50 would be 10%. So can the sample students be treated as independent? No, they cannot. All right, let's take a look at solving at least once problems by using complements. Sometimes we need to find a probability of an event that occurs at least once in several independent trials. We can calculate such probabilities by finding the probability of a complement and then subtracting 1. So we're going to look at 2 examples to illustrate that. A fair coin is tossed 5 times. What's the probability that it comes up heads at least once? Okay, let's take a look at this. Solution. The tosses of coins are independent. So since the outcome of a toss is not affected of the outcome of the other tosses, the complement of coming up heads at least once is coming up all 5 times. So we're going to use the complement rule to compute this probability. So what is the probability that it comes up heads at least once? So the complement of that would be 1 minus the probability that it does not come up heads at all, which is 1 minus the probability that it comes up tails all 5 times, which is 1 minus the probability that the first toss is tails, the second toss is tails, etc., till the fifth toss is tails. So that would be 1 minus the first toss being tails times the probability that the second toss is tails, etc., and the fifth toss is tails. So that would be 1/2 to the 5th power. Now, where did I get the 1/2? The probability that I would have tails when I flip a coin is 1/2. The probability that I would get tails all 5 times, is going to be 1/2 to the 5th power. So I'm going to take 1 minus that, which is 1 over 32, and I will get 31 over 32. And finally, find the probability that an event will occur at least once. Items are inspected for flaws by 3 inspectors. If the flaw is present, each inspector will detect it with a probability of 0.8. The inspectors worked independently. If an item has a flaw, what is the probability that at least one inspector detects it? The complement of the event that at least one of the inspector detects the flaws is that none of the inspectors detect the flaws. We use the complement rule to compute the probability. We begin by computing the probability that an inspector fails to detect the flaw. So the inspector fails to detect it. That would be 1 minus the probability that the inspector does detect a flaw, which would be 1 minus 0.8 as given above, which would be 0 2/10. So at least one inspector detects the flaw. That would be the complement of 1 minus none of the inspectors detecting the flaw, which means all 3 inspectors fail to detect a flaw, which means the first fails, the second fails, the third fails, which means the probability of the first failing to probability of the second failing, probability of the third failing. Now, we already calculated that the probability of an inspector failing to detect the flaw would be 0.2. These two are going to always add up to 1. So I would take 0.2 to the third power, then subtract it from 1, and the probability that at least one inspector does detect the flaw would be 0.992. Okay? All right, well, that was actually the last example in section 5.3. Now, I realize that there is a lot going on in these sections coming up. My big suggestion to you would be that you start using 3x5 cards to separate what kind of problems they are and go through those 3x5 cards regularly so you can remember them. Now, lastly, I want to go over this nice conditional probability model that looks at mutually exclusive and independent events. Okay, so does an event involve and, or at least? If it involves and, you're going to ask, are they independent? If they are, you just multiply the probabilities. If they are not, then you multiply the probability times the condition that B will happen given that A will happen. If the probability involves at least, then you're going to take 1 minus the probability that none will happen. And if the probability involves or, are they mutually exclusive events? If they are, like section 5.1 said, you would just add the 2 together. Or if they're not mutually exclusive, you'll have to subtract your overlap. Okay, so this is a nice way to remember which one to use. And it will get confusing especially if you have not studied statistics before. So you're going to have to take some extra time and write down what the actual conditions are, whether they're independent, mutually exclusive, and for you to keep track of how to do what. Okay? All right, that's it for 5.3. I'll see you for 5.4.